Welcome. Well, today's video is about the second of three experiments. I've already explained the first one and given the results, which were quite good, even though I wasn't looking for precise values. I was comparing whether the voltage on a given resistor was larger or smaller, not what its value was. This one is a bit different. This is the one where I'm trying to determine the two constants of my equation. Okay, the two previous videos are called the three circuit experiments. This is experiment number 1 using 3 resistors. And then the second video I did was the results of that experiment. And I got, of the two parts, I got very good results, 70% correlation and 80% correlation, or better. Very encouraging. This was not going to be so easy. So these were the three that I first explained. I was trying to show that shielding, which is a mechanical effect or a gravitational effect, was evident in a circuit with 3 resistors. The second one, which I'm explaining today, is to find the constants of the TPM circuit equation. And my next one, or one of the events in the near future, I'll talk about parallel resistors. Well, this particular experiment goes back to an experiment that I have known about for quite a while. There is a gentleman from, he was an Italian, Quirino Majorana, if you want, or it's Quirino Majorana, if you want to pronounce it correctly. He was an Italian experimental physicist, and he looked into a range of things, and he was a professor of physics at the University of Rome in Turin, Italy, and in Bologna, in Italy. And in particular, he performed a long series of very sensitive gravity shielding experiments. Notice the shielding, which is what I did for the previous experiment. And he did those around, as you can see, around the 1920s. And they've never been reproduced, although I used his experimental results and I did the calculation of the two values that I need for my gravity equation using his experiment. So I was quite familiar with it. And his experiments determined that mercury or lead around a suspended lead sphere acted as a screen and slightly decreased or increased the Earth's gravitational pull. That was the purpose of that experiment. Well, this is the drawing I did way back then, and it shows only one of the experiments. He had a lead ball, and he, in a sense, measured it in Earth's gravitational field on a balance. Then he interposed a lead cube, and he actually did 3 different ones. He did it with the lead ball on top, with the lead ball in the center, and with the lead ball below. And there are results of those experiments. This is the one I'm going to use in explaining the 2R, 3R experiment. And it's a 2-part test. He took a 1.274 gram lead ball on a Ruprecht analytic balance, a good balance at it in its day. And this involved the earth and the lead ball, and I'm highlighting the fact that it's 2 components, and hence I'm going to replace that with 2 resistors. The second part, then, he added a lead cube shield such that the lead ball was above the shield in this case. This involved the earth, the shield, and the lead ball, and that's 3 components, or in my case, 3 resistors. And Majorana was able to calculate the constant for his gravity equation, and I calculated the constants for my equation. I consider those values quite preliminary and have not reported them until more experiments can be done. Okay, so the TPM circuit equivalent, first part, use a large resistor to model the earth and a small resistor to model the lead ball. That's the 2R circuit. Second part, add a third resistor in between the large and small resistors to emulate the shield. That's the 3R circuit. Question is, can I find the constants of the TPM equation for circuits? So let's look at that. Here's the two circuits. I use a 9-volt battery in particular. This is labeled the 2R circuit with resistor 1 and resistor 3. Resistor 2, the shield is missing. So we're going to measure the resistances, measure all the voltages. And this is the 3R circuit. You add the R2 resistor as the shield, and you measure all the resistances, measure all the voltages. And basically what I'm saying is the R1 is the earth, it's a large resistor. R2 is the shield, it's a medium-sized resistor, and the lead ball is a small resistor, all based on Majorana's experiment. Now here are the equations for the 2 resistor circuit. And the voltage drop across each resistors, the resistors are based on the number of G1 particles entering the resistor. Entering resistor 1 is B. Entering resistor 3 is D. So it's proportional to the number entering. It's proportional to the percent interacting with the resistor. The larger the resistor, the greater the interaction. But this becomes one of the constants that I'm looking for. But these first three terms basically calculate the number of G1 particles lost going through this resistor. In order to get a voltage, I invented a constant that is the volts per G1 particle. So this is the number lost. This is the volts per the number lost. Hence, that's the voltage lost across resistor R1. This is the voltage lost across resistor R3. B2 and D2 are also unknown. I don't know how many are flowing. Basically, in my spreadsheet work, when I've set this up, by setting a value here and a value here, I do find these numbers, but I don't know what this precise number should be. The third voltage equation is the sum of the voltages around the circuit. That's Kirchhoff's law. Says that the voltage drop in the 2 resistors should equal the voltage of the battery, or the sum of the voltage around the circuit must equal 0. So what I end up here is 3 equations with 4 unknowns. I got 4 unknowns. You can't solve that. There's no way to take those 3 equations and solve for 4 unknowns with 3 equations. Note, these are simple algebraic equations. Well, here's the same thing for the 3 resistor. But this time I got the voltage drop across all 3. I didn't say this before, but the previous was B2 and D2. This is B3 and D3 to distinguish them because they're not the same, or at least you can't guarantee they're the same, and it turns out they're not. So you got the 3 voltage drops across the resistor. You got Kirchhoff's law, which involves the sum of all 3 resistors equaling the battery. And now I have 4 equations and 5 unknowns. That's 5 unknowns. So you can't use these 4 and solve for anything either. But IF, the interaction factor, and the volts per G1 is or two, but you don't have to count them twice. So what happens is I end up with 7 equations and 7 unknowns. These are the two I'm looking for. Interaction factor, volts per G1. B2, D2 are from the 2R experiment. B3, C3, and D3 are from the 3R experiment. I'm still working on the solution. You'd think, well, this is just simple algebra, just grind it out, you got it. But my experience with this process is you got to find the right sequence and do things in kind of a very proper, effective order that gets you there. And I've been working on this for days, and I've got sheets of paper all over the place, and I'm not there yet. However, when I get the equations done, if you remember, I have taken measurements of 15 sets of resistors. And part of that measurement that I made involved the 2R, 3R measurements. So I will end up with, I will have 15 different sets of values to apply to these 7 equations with 7 unknowns and get 7 different answers. Now, if you remember my experiment number 1, even though it's a simpler experiment, I only got 70% or 80% correlation. Some of them didn't work out. Well, that's the same, these are the same measurements, same resistors. And so the ability to get 100% here doesn't sound very good at all, because I'm limited already by knowing that the other ones didn't work. Well, this one, to make matters worse, this requires on the accuracy of the measurements. The values are now important. And if the values aren't right, not going to be good either. So this is not an easy result. Well, get the equations, apply these values, see what happens. So I'm going to find the 2 constants. And the reason I say that, this is just to explain why you can get an answer in this case. If I have 7 unknowns and 7 equations, here's a case of 2 unknowns and two equations and 2 unknowns. X and Y are the unknowns, and I got this equation and this equation, and I should be able to find these 2 values, assuming that X is VG1 and Y is IF. You know you can do it. So I expect to be able to get equations for VG1 and IF. This is just standard algebra. Okay, here's my expectation. The first experiment compared whether the voltage value of the large and small resistor were as placed in either the first or last positions were higher or lower, and I ignored the values. These are the percentages. I rented a 6.5 digit meter, and I'm hoping it's accurate enough. There is a meter that's 7.5, and it costs twice as much to rent. If the results are not, if it's not accurate enough, maybe I may only get 50% correlation or less. Expectations aren't very high unless my meter is accurate. Then maybe I can get some real values. See what happens. Yes, I'm still working on it. I don't know when I'll get this done. I don't know when I'll report on the results. But I am working on it. And when I get it done, my plan is to present the data, right or wrong, whether it helps my model or not. Got to report the results. And my hope is that it does. It worked for when I used this idea using Majorana's experiment. in gravity. I'm hoping it's going to work here. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.